Good. Good evening, everyone, and thank you very much for joining us in this our new session that we present in the context of the ArchiFridays events that we have every Friday from 12:30 to 13:30 p.m. Paris time. And this is our opportunity, in fact, to present a special guest every week with a special topic to explore the latest trends and technologies, best practices that we have in real world applications and insights for solution architecture and also for cloud design. So those events are dedicated for those who are interested by those topics, whether you are experienced architect or you are a developer, or you simply are just passionate about those techniques and technologies and building modern and scalable systems. So this event is for you. So today we will dive into a topic, a very interesting topic. We have a special guest for us with us today, and we will try to go back to the different technologies that we can cover in designing enterprise solution architect. And of course, we welcome your questions. We welcome all the comments that you can make on our live sessions that we have on LinkedIn or even on YouTube. So I will give the time to my friend Rodrigue, who is co-animating this session. So as usual with me, to present our special guest, to present the topic. And of course, we will give the time to Varshini to present and expose the topic. So Rodrigue.
Okay, thank you, Semi, and hello everyone, and welcome to this weekly ArchiFriday session. As Semi said, ArchiFriday is our weekly series where we explore key topic, lesson, and experience from leading experts and anyone who want to share some experience in architecture and technology. Today, we had the pleasure of hosting Varshini, who will share her experience and insight in a session titled Lesson from Building Your Real-Time Machine Platform. This is a unique opportunity to learn how scale real-time systems are designed and operate in one of the most challenging environments in the industry. So thank you again, Varshini, for joining us and for accepting to share your lesson with our community. Varshini, the stage is yours. Thank you.
Okay. Thank you, guys. Thank you for your introductions. Let me share my screen
Yeah.
and start presenting.
Good, we can see
Yeah.
everything.
I hope you guys can see my screen.
Yeah.
Okay. Yeah. So, good evening, everyone, and I thank you for being here. My name is Vaishni Chaudhary Nubla. I am currently working as a cloud infrastructure DevOps engineer with my strong focus on infrastructure as a code and native architecture. I am in my current role. I support working with automating the cloud environments, managing and securing the access through the single sign-on workflows, and also ensuring our infrastructure remains scalable, really, resilient, and also compliant with the AWS architecture. Over the past few years, I have been fortunate to work and gain experience across multiple industries, including the finance industry, healthcare, and retail. I have helped organizations move from the legacy systems to the modern cloud architecture, from building the monitoring dashboards in Grafana to deploy the predictive systems or Kubernetes clusters. And also, I work. My focus would be mostly consistent goals, making the systems faster, also safer and smarter through the automation. Academically, I hold a master's degree in IT from the University of Cincinnati, and I'm currently pursuing my MBA at the University of Cumberland, specializing in the project management. This combination of technical depth and also the business insights have really shaped on how I approach the architecture, not just from the engineering lens, but also from the value and the impact perspective as well. Today, I'm excited to share, a case study which emphasizes these principles over real-time matching platform, where we explore how the architectural vision scaled to serve million globally, and what lessons we can carry into our own systems. So let's begin. So I am honored to welcome all of you to the session. And today I will walk you through the remarkable journey of how the Uber transitioned from a basic riding matching system that responded in seconds to one of the world's most sophisticated real-time platform, basically that operates in milliseconds. This isn't just a story about like how the technology is evolving, but also it is like an innovation. While this case study about Uber is like the patterns and the decisions and the lessons that are highly transferable. Whether you work in the cloud infrastructure like the data driven platforms or the complex service delivery, this session will actually give you something valuable to take back. Coming to our agenda, let's dive into these details. The roadmap of the today's talk. We'll be starting looking at the evolution of the Uber architecture, moving from a simple monolithic application to a highly distributed real-time microservice-based architecture. Next, we will look into the architectural components that enable the real-time performance, including the prediction systems and the dynamic pricing as well. Then we'll be exploring to the practical lessons on learn throughout the journey, the principles that apply not just for the Uber but also for the large scale systems. After that, I'll walk you through the implementation strategies on how the Uber adopted to reach the scale, including the hybrid cloud and also the hardware tuning and global edge presence. And finally, we will look into the future with trends like edge computing, quantum-inspired algorithms, and also the anonymous infrastructure. My goal here is to share the technical but also actionable ideas that you can also apply to your own systems and teams. Next, let's begin with the problem statement. Uber process like millions of rides daily, more across more than like 10,000 cities globally during peak times. It handles over like 1,000 ride matches per second. Every one of those matches has to be accurate, fairly developed, and it has to be delivered under like 100 milliseconds. The system was maintained, 99.99 percentage of availability to adapt to the rapidly changing supply and demand. Uh, and also it has to ingest the billions of location updates. The challenge isn't just about scaling, it is also the scale and the precision and also the speed in the real world across the globe. Next, we will dive into the Uber story. Started like many startups, with a monolithic architecture, simple, quick to build, and effective for early growth. But as demand grew, the model showed its limits. Between 2013 and 2015, Uber began, decomposing the monolithic into discrete services. The rider and the driver functionally were separated. Geolocation services were split off. Redis was introduced for faster, caching. By 2016, Uber moved to a distributed architecture with Kafka enabling real-time event streaming and also a more specialized data stores. And by 2019, the platform became a fully optimized real-time matching system powered by predicting and also implementing the machine learning capabilities of the decision making. This wasn't just like a one-time rebuild; it was like an evolution where each phase was solving the problem of its previous one without disrupting the business. And next we have the Uber's architecture. These are like the key architectural components, which are specializing the components that work together, like in the clockwork. We have the geospectical engine that uses the hierarchical indexing to find the nearby drivers with milliseconds. a matching service that balances proximity and also estimates the arrival time and also the driver preferences, even the rider history. A price engine that dynamically adjusts the fares in the real time and also the local supply and demand. Prediction systems that forecast the future demand and also enabling the proactive decision making. And finally, a resilience layer which is built in a fallback mechanisms and regional isolation to ensure that 99.99% availability. Each piece is optimized for its function, but designed to integrate tightly within the ecosystem. Next, let's dive into one of the Uber's biggest technical hurdles was geospatial querying at scale. With millions of users constantly moving and updating their locations every few seconds, traditional databases couldn't keep it. To resolve this, Uber developed a custom in-memory spatial indexing system using the H3A hexagon-based hierarchical grid. This approach allowed the systems to divide the world into cells that perform rapid lookups and also distribute the load geographically. This results like a sub millisecond response even during the peak activity. Next, let's dive into the real-time market balancing algorithms. Matching a rider with a driver isn't just the beginning. Ensuring the market balance is even more complex. Uber uses three real-time strategies. The first one is supply-demand detection. The system continuously monitor ride request and availability drivers in each location, analyzing like 30-second sliding window. And the next comes the dynamic pricing. Machine learning models adjust the fare to influence the rider demand and the driver supply in real time, all based on the geospatial heat maps. And the third comes the driver, repositioning. Ideal driver receive recommendation to move to high demand zones backed by the positioned earning and behavior insights. Together, these mechanisms basically help healthy supply and demand ratio across thousands of micro market in real time. Next, we'll go over the prediction systems architecture. Uber doesn't wait for demand to spike; it predicts it. Their forecasting engine basically ingests billions of trip records, weather data, traffic signals, and also the local event calendars using the time series models like LSTMs and grid boosting the techniques. It also produces like minute by minute demand forecasts, sometimes hour in advance. These capabilities enables the proactive driver placements and reducing the rider wait times and also increasing the overall system efficiency. Next, we'll go over the infrastructure evolution strategies. Supporting all these requirement bold changes in infrastructure. Uber uses a hybrid model, keeping the core services on its own data centers while using the cloud for elastic capacity. It invests in the cloud, the custom hardware, including the NUMA aware servers, and also it uses the GPU for inference tasks. A global edge network routes, usually we use it for the user request through over 45 points of presence, minimizing the latency and also ensuring the regional resilience. As an outcome, 42% of reduction in infrastructure costs while supporting like a 5x more traffic. Next, we'll walk through the achieving millisecond response time. Millisecond performance doesn't happen by chance. It is engineered. So Uber applies like the deep performance optimizing techniques like data locality ensures that the computations happen close to the data, memory tuning, and also cache aware algorithms to boost the performing speed. Lock and also it has like lock free data structures where we have the custom network protocols and also the asynchronous pipelines to remove the bottlenecks. Even the minor optimizations like avoiding the garbage collection during the peak hours make the significant impact.
Okay. Sorry, Marshini, are you sharing your screen? I don't see anything.
I am sharing.
It's okay for you, Sydney? I don't see anything.
Oh, I thought I was sharing my screen. Oh, is it okay?
Yeah, now it's okay. Thank you.
Okay, sorry about that.
No, you're welcome.
Okay. Do you want me to continue, guys?
Yeah, it's okay. You can go on. Thank you.
Okay, thank you. Okay. Yeah, so here we are at achieving the millisecond response time. So, as I was mentioning, even at the minor optimizations like avoiding the garbage collection during the peak hours, it really makes a significant impact. Next, we see the performance metrics like before and after. Let's talk about numbers. Matching the latency drops from the several seconds to milliseconds. 41x improvement daily request scaled like 12.5x. Billions of data points are now processed in real time. These improvements didn't come from like a single innovation. They were the result of the layered architecture decisions made over several years. So next we'll walk into the key architectural lessons so that we can take away from all of these. So we have the data locality matters. So bring computation closer to the data and not the other way around. So we have the heterogeneity is powerful, like it is tailored for each component of these roles to avoid one size fits for all solutions. It is designed for failure, built for degradation, not just the uptime. We like measuring everything like observability isn't just an option. Uber collects over like 1.5 trillion metrics daily. These principles are universal and can be applied to nearly like any large scale systems. Next, we'll walk through the like these lessons are drawing from Uber. These relevant span has like multiple domains. Finance, which has like high frequency trading and also the fraud detection, require a similar real-time systems. IoT, which has like a device tracking, telemetry, and also the predictive maintenance for all the benefits of the geospatial and also the predictive modeling. And we have the e-commerce, which is like a demand forecasting, inventory management, and also like the delivery routing uses the same core principles. The smart cities, which has the real-time traffic flow and also the emergency routing, and we have the resource allocation for the minor Uber's logic. These patterns are reusable and also increasingly essential. Next, we'll dive into the real-time architecture going next. So the edge computing will move matching logic closer to the Uber at mobile towers or the edge nodes, reducing the latency even further. The quantum-inspired algorithms are already being tested to solve the complex matching under these constraints. Self-managing infrastructure is emerging with the AI optimization capacity, like the tuning systems, and also handling the outages like anonymously. These trends are also exciting, and they are like closer than many of us even realize. So the key takeaways here are like the architecture is a business enabler. The Uber's growth was powered by the technical evaluation. It was powered by the technical evolution, and also the progress is it is not waiting for the perfection. It has the improvable consistency, and also it is optimizing your domain. It has like generic systems won't beat domain away from the design, and also it has the cross It accelerates the innovation. So I think these are the key takeaways from the architecture of the Uber. Yep. Thank you for your attention, and I would be very happy to answer any of your questions.
Yeah, thank you, Varshini. We have six questions. I will take this question one by one. The
Okay.
first one is related to the real-time performance. You hear me?
I can hear you.
Yeah, thank you. The first question is related to the real-time performance. The question is what were the main architectural patterns that enabled reducing response time from second to millisecond while still processing millions of concurrent requests?
Uh, so you're asking what are the main architectural factors that are enabling to reduce the response time?
Yeah, sure.
Okay. So right for basically reducing the response time from seconds to milliseconds while processing the millions of component requests, we typically have this combination of the architectural innovations and optimizations. We have like significant architectural factors that contribute to this significant improvement. We have like horizontal scalability with load balancing, where we have like distributed systems. The applications will break the application into like multiple instance or like the microservices that can run concurrently. And also we use the load balances with the horizontal scaling, which we use like smart load balancers to distribute the requests evenly. And also the next factor would be like the microservice architecture. We split the monolithic app into smaller and independent deployable services, where each service handle like specific type of the component request to reduce the overhead. And the other we have is also the caching of multiple layers. So basically, we use like the edge caching and also the in-memory caching to avoid the repetitive database and also compute the heavy queries. And we also have the local caching, where the components or the recent queries are locally when possible. And we also use like the optimized data access layer, where the database replicates to serve like the ready heavy workloads, and we ensure that the queries are using like the right index and written effectively. So these are few factors that basically determine uh, you know giving the high performance.
Okay, thank you for your answers. And the second question is about predictive model integration. And the question is how are predictive algorithms integrated into the matching process to anticipate demand and optimize driver positioning in real time?
Okay, if we're taking Uber as an instance, here for the predictive algorithms, so we have the matching process of the real time driver positioning, the demand anticipated for the core aspects of the modern ride sharing. We have the feature like the logistics and also the mobility platforms, where we anticipate where and when the demand will arise, and also position the drivers proactively to minimize the rider wait times and also the driver ideal time. So here we use like the real time horizon historical data which is constantly ingested. So it uses like GPS, real time location, and also status of the driver and vehicles. We can use the rider request to pick up and drop off the points, and also check for the cancellations. We use traffic and weather. We use the current conditions impacting the supply and demand. We can check the event and also the calendars, where sometimes the concerts, sport games, or holidays might take place. So those are some of the urban patterns that we can take care of. And we also have like the demand forecasting models, where we predict the models to estimate the future rider demand for specific locations. So for those, we have like multiple algorithms that will be used, like time series model, or they also use like the deep learning, and also the hybrid ML models, which are like machine learning models, which are used for the clustering. And we also use like the driver repositioning optimization, where the system it basically predicts the demand of the predictions of the system of the repository of the drivers, like where where are they passively waiting for the request. So these are some of the real time use cases where we try to check the continue for the continuous improvement of the predictions and strategies. Yeah, these would be the core principles.
Okay, thank you. Thank you for your answer. I have another question. It's about the data pipeline architecture, and they ask what kind of data architecture supports the ingestion of processing of billion of data point in near real time for forecasting accuracy.
Sure. So in real time, forecasting the data would, like it is through the process of, the data points, like we have to, like, it has to be ingested and processed like billions of data points in the real time for forecasting, especially in the context of like demand and prediction, for positioning the drivers. For a robust and also the scalable data pipeline architecture is very essential. So the architectural components has like certain principles of it. To break down, we can start with the data ingestion layer, where this layer basically collects the massive volumes of data from the multi-source continuously, and also to scale it. It also uses the source like GPS, also the telemetry data from the mobile devices, and also the weather APIs, traffic feeds. It also uses like the event databases uh, for determining the calendars, like the concerts and holidays, and it uses like basically the technology like Apache Kafka, and also it uses the custom event ingestions. Next, we would have like the stream processing as well, the ETL layer, where we process like the raw streaming data in real time, and also it applies to the transformation and creates like a feature data sets, which is helpful for data cleaning, and also it is really essential for checking the demand scope, and also the rider density, what would be the grouping GPS pings per trip, those kind of stuff. And we also have like the feature store, like where we have the features are stored to use for the forecast models, both in real time and also for the batch models. uh, and also we also have the real time forecasting, where the forecasting models are deployed, and also which are queried continuously with the fresh data to output the demand and supply predictions, which are really useful to predict the low latency and also the high through output of the city scale prediction during the rides. Yeah, so I would say these are some of the key architectural characteristics, like the high true output, or the low latency, and also the high scalability, and the modal adaptability, which is has like the continuous learning pipelines. So yeah, these would be the key architectural features, I would say, for forecasting.
Oh, okay, thank you. Maybe the last question in my side. You have a question, Semen? The last question for me is the real-time and edge performance. So, what architectural criteria guided the decision of which process run in the central cloud versus at edge nodes?
Sure. So for the process that how the so you're asking how the edge nodes work for this particular model, or?
Yeah, because maybe I'm wrong. I understand that some process run on edge nodes and other are running in a central cloud. So the question is, what was the criteria that guided the choice to make some process run on the edge side and other on the cloud central?
Okay. Uh, So coming to the, so some processes, basically run on the edge nodes, and the others certainly are, centralized in the cloud. So the decision where to run the process is like a strategy, I would say, which has the hints on the latency, bandwidth, and also the data volume, also the cost and the real time, constraints. So the key, here is to govern the principles behind, deciding where to run the edge, the cloud, basically where to run the edge. So we have, like, the data gravity, and like, which keeps the process close to the large volumes of data which is generated. And we also have, like, the latency sensitivity, where we process, that request must operate within the consistent connectivity to run at the edge. How the edge nodes are typically, leveraged in the system, forecast the demand and optimize the driver positions. uh, so these functions of the latency critical depend on the fresh local data, and also it helps to reduce the cloud processing and the bandwidth. So yeah, so cloud centralized responsibilities, like, they function on the large scale demand forecasting, and also the global driver supply modeling. And they train and also retrain the ML models we use, like the global load balancing, to load balance and also coordinate the regions to prevent the driver saturation. We also have the model performance monitoring to evaluate and also deploy, like, updated models to edge nodes. Uh, yeah, so uh, why cloud? I would say that these require, like, the heavy computation, and also for the global context, like long history or high data volumes that edge drivers can't handle. Yeah, so in summary, I would say basically the central principle, is, like, run latency sensitive local data bounding and lightweight logic at the edge, to run heavy globally informed, and also to coordinate the the processing of the data. We can use, like, the cloud edge architecture. So this is like a hybrid edge cloud architecture, which enables the scaling and also to use for the real-time systems to perform the predictive modeling for the drivers to optimize at the global scale.
Okay, thank you. Any question, Seme? We don't hear you.
Of course, I just wanted to let you finish with your questions, and then I have some few questions. Yes, but first I wanted to thank you, to thank Varshini very much for being in this session, and especially we know the time constraint that you have from your side. So I think that actually
Thank
it is
you.
about 6 a.m. 30. So once again, thank you very much for joining us for this ArchiFriday session, and for your dedication. The topic is very, very important, especially to explore what we have as architectural evolution that is behind Uber's real-time system that is actually running for the entire solution, and especially to move from that previous, or let's say historical monolithic system, to the new microservices systems. And starting from here, I'm not going to go into the deep details of the solution, but you already mentioned that the transition from the monolithic system, or the historical and previous architecture, to a microservices architecture that is actually set up, played a key role in reducing the latency that we have actually in the architecture. So my question is just if you can elaborate, or just give us the most difficult trade-offs that your team faced during that transition. So particularly from moving from the monolithic system to the microservice systems, including, for example, the service orchestration, any trade-offs related to data consistency, to deployment complexity. If you can resume those points in, let's say, two or three points, main points, and main trade-offs to move from the first architecture to the second implementation in the system. Can you elaborate more on those 2 points?
Yeah, yeah, definitely. So I think yeah, that is like a really good question to answer. Moving from the monolithic architecture to the microservice-based architecture is like a major architectural shift, I would say, to bring the big performance and scalability benefits. But like here are like but we would without trade-offs, there won't be any kind of system that would be going. So I would say that especially with the system handling the real-time predictions and also the driver positioning and also like the high demand forecast. I would say like the benefit of like this service or orchestration versus simplicity would be like microservice decomposes complexity, which allows like smaller teams to own and also scale and deploy the services independently. This is like a modular which enables like the parallel development and also the latency optimized services. uh, and also for this particular one, I would say the trade-off would be like orchestration will become like a major pain point where we want for a single code base with asynchronous function calls to for the distributed systems. So basically that needed like the API gateways, so the service discovery. We would do the retry logic, and also we have like the circuit breakers, and also we'll have like the distributed tracing. So I would say like so basically for each of it, like there would be like a single function, a call that allows like 5 to 7 services, which has like pricing, availability, routing, ETA. So each has its own failure points and also the latency issues. The solution here would be like adopting the orchestration platforms like Kubernetes and also implementing the service mechanisms to make this architecture resilient, I would say. And the next one I would say would be like the data consistency. In the microservice architecture world, each service has its own data, which supports like independent scaling and also the faster local access for the critical, reducing of the latency. The trade-off for this would be like the data consistency and the duplication, I would say, which will actually be very difficult to manage. The data duplication and also the data consistency. For example, I would say like when we have like a demand forecasting service like driver states, like the trip matching services, all the driver has need to have some shared view of the driver's location, but also maintaining like a single source, for the longer trivial. So here the issue we faced is like we have the rare conditions due to the uneven eventual consistency, and also the larger gaps between the maybe the message queues, and also the replication of the data delay could happen here. Yeah, so and also we have like the operational complexity. I would say like the microservice architecture gives us the ability to deploy the different parts of the system independently, where we have like the key for the reducing the latency, and also the iteration on the performance is critical for the services. So here I would say the trade-off for the operational would be the complexity exploded. So we have like the versioning issues, or we might have the rollbacks become harder across like the dependent services, and also we have like the CI/CD pipelines which needs to be handled for any atomic rollouts. Yeah, so these are some of the complexities that I would think of.
Yeah, yes, thank you very much for this answer. So Yes, orchestration is very problematic and trade-off in setting up those kind of architectures and solutions. Added to that, the complexity that we may have for the data and the different types of, let's say, operations and processing that we can apply to the data, as you mentioned, especially for maintaining the data quality, cleaning the data, and getting this kind of let's say unique data management approach. And starting from this, we have also, you have mentioned that you also have for that predictive analytics, let's say algorithms or let's say solutions that you have implemented. Of course, behind we have those deep learning, machine learning algorithms that you deployed for operational requirements. And we know that with those solutions, there is a great, let's say, or we need to maintain a certain balance between the requirements for having a low latency solution, and also the need to process this huge volume of data that we have, especially also by implementing, let's say, heavy models that require a lot of pre-processing, like a lot of capabilities or computing capabilities. And how did you manage, or how did you handle that constraint of this trade-off too, in order to optimize the solution, the global scale of the solution, especially when you implement those, let's say, predictive analytics, and including machine learning, deep learning, and those type of solutions. So we know that they are already consumed from already pre-trained models, but are there any, let's say, pain points that you encountered during setting up those solutions, and how you face it, those type of constraints?
Yeah, sure. So basically, for the core architectural, for building the real-time or like the large-scale AI systems. So, we have like both the operational performance and also like the analytical depth that we have, especially when, we are processing like, billions of events, and also which requires like the sub-second response, and we're using like complex ML and the DL models. We have a few effect like most effective strategies that we adopted to reconcile it. So basically we use like decoupling serving for the training, to train like the heavy, and also the serve like light, separate heavy models workflows from the real time path. Basically, we have like the training pipelines to run on the massive batch data sets. Using like the Spark, we use tools like Spark. We also use the TensorFlow, etc. And these models are basically, compressed of the smaller versions, and these are like the lightweight versions which are deployed on the edge nodes, or the low latency, serving the components. So basically, we'll have like the full model of accuracy with this, but the latency remains within the the target bounds basically. So this reduces the the resource footprints, allowing for the horizontal scaling. And the other one I would say would be like split the interference strategies, like using the multi-tier architecture, which has some predictions happen centrally, and also like the batch forecasting, which is done at the regular intervals, and the real-time interface where we have the final, which is used for the cache predictions as a context. And we also use like the feature of engineering pipelines with the pre-processing on the edge, where we basically push the basic processing the into the ingestion, or like we basically do the enrichment, where we can have like the data originates, and we avoid shipping the massive raw data to the cloud. In Like we keep the cloud analytics focused on the model computations, and also not the raw data basically ingesting to the cloud. So yeah, these would say, I would say, like these are some of the constraints or trade-offs, or like the heavy models versus like the low latency, real time freshness versus the cost of the processing, and also like the the feature complexity versus like serving the performance. Yeah, so these are some of the trade-offs and the solutions, I would say. The architectural balance was actually really about putting the right workload in the right space, I would say. Uh, Cloud for the heavy lifting things, and also for the deep learning. Maybe edge for the lightweight interfaces for the pre-processing and real-time responsiveness. Yeah, so yeah, these would be the architectural balance.
Good. Thank you, Varshini, for all those details. So, Rodrigo, I don't know if you have
No, no,
any additional question.
no additional question. Do you hear me?
Yes.
Yeah, we can hear you.
Yeah, thank you. No additional question. We are close to the end of the session. Maybe Rashid will have something to say or any additional information you need to give us. So on my side, what I can say is just a big thank you. A big thank you to you, Bashini, and your team for sharing the experience and insight with us today. This session gives us, I think, a great perspective on real-time architecture at scale. And for additional question to continue the discussion to our audience, feel free to reach out Varshini directly, or you can through our usual architecture brief, if I can say. And maybe Varshini, we also like to ask if the slide can be shared with the community for reference. And yeah, just for a quick reminder, ArchiFriday, as Semi saying at the beginning, is an open community event, open to everyone, whether you are an experienced architect or simply curious to learn. So with that, I will hand it over to my co-host Semi for the closing words. Thank you.
Yes, thank you very much, Rodrigue. That was a great pleasure for me to have you, Vershini, with us today for this session. Once again, I know this is a big commitment from you, especially for the local time zone. And we know, I know that the topic you covered today is very complex, and only 1 hour is not enough, not sufficient to take all the points that should be discussed or that should be shared with us for this training for this today. And of course, we still open to any additional, let's say, participation from your side. We will contact you in order to have you with us in upcoming sessions and to let you, in fact, even talking about additional aspects, not only for the solution that we have actually for Uber's infrastructure, but even your insights, your experience, recommendations, best practices that you can provide. So this is really important. Besides the use case that you shared with us today, and many of our followers and are looking and searching for information and this type of recommendation. So once again, thank you very much. I'll let you have or say any last words for this before closing the session.
Yeah, yeah, sure. Thank you so much, guys. Thank you for your time, and it was really great meeting you both. It was, the questions you guys asked was really, at right, at right time and right questions, and yeah, everything was so good. Yeah, you guys can
Thank
reach
you.
out to me anytime through LinkedIn or through email
Sure.
for any further questions or details regarding the presentation or anything else.
Sure, of course, we have your contact, so we are not going to miss that. So to be honest. Okay, so thank you very much. So Varshini, for your participation. Have a nice day, and see you maybe for our upcoming or our next sessions. Thank you very much.
Okay, thank you.
Thank
Thank you
you.
for your
Thank
opportunity.
you.
Thank you. Thank you.
Bye.
Bye. Bye.
Bye.